screen?
Yes and yes. Looks good. Thanks.
Okay, thank you. So today I would like to talk about the new ocean research analysis dataset. The name is LETKF-based ocean research analysis, LORA, in the Western North Pacific regions. I am Shun Ohishi and a postdoctoral researcher in Riken, Japan. So let me first talk about the recent development of the satellite observations. So as you know, the number and types of the satellite observations has been increased recently. As shown in this movie, showing the sea surface temperature in the Indo-Pacific regions, the Himalaya-8 satellite, the geostationary satellite, has observed the sea surface temperature with high horizontal and spatial of minutes and since June 2010. And also, so far, the satellite observed only the one-dimensional sea surface height anomaly, but now the SWOT satellite are planned to be launched since November 2012, 22, and observe the two-dimensional sea surface height anomaly. So this recent satellite development provides us the motivation for frequent data simulation. However, the frequent data simulation would be challenging because data simulation provides the analysis with a dynamical imbalance generally. So dynamical imbalance results in the initial shocks with high frequency gravity waves. So if we conduct data simulation at a high, the frequent interval, the initial shocks might be accumulated and might degrade the accuracy of the analysis. So we have constructed an ensemble Kalman filter-based ocean data simulation systems and explored optimal settings for the frequent data simulations. So we have found that the most suitable setting is a combination of the RTPP, the relaxation to prior perturbations, IAU, incremental analysis update, and AOEI, the adaptive observation error inflation. So here I only pick up the I only take the example of the impact of the AOEI. So these figures show the salinity at the sea surface and the cross of the this 150 degree east across the Kuroshio extension regions. I performed the control run without AOEI since July 2015. So after the 5 months later, so we have found that the low salinity structure in the intermediate layer is broken. However, if we implement the AOEI, this low salinity structure is improved substantially. And I forget to talk about the AOEI, but the AOEI is a method to adaptively inflating the observation error using the innovation statistics. So finally, I would like to introduce the recent status of the ocean Lianas dataset. So this table summarizing the Lianas dataset. In the top table summarizes the global Lianas dataset, and the bottom table summarizes the high resolution regional Lianas dataset in the Pacific regions for each assimilation method. As you can see, the 3D bar is now commonly used in the ocean community. However, the ensemble Kalman filter is rarely used in the ocean data simulation system. And here, PODAS is one of the choices of the ocean data simulation system. But this PODAS has a data transmission interval, relatively long data transmission interval of 5 days, and in which temperature and salinity is only assimilated. And this dataset is not currently not available. So therefore, as far as we know, there are no high-resolution ensemble chroma filter-based realistic dataset with frequent data assimilation in the Pacific regions. So our motivations is to create a high-resolution ensemble chroma filter-based ocean research analysis dataset in the Pacific regions, and to compare the validation results from the created analysis dataset, that is the LORA, with the existing analysis dataset and observational datasets. So again, the dataset I created is the LORA, the LETKF-based ocean research analysis, which conducts the daily three-dimensional analysis ensemble mean and spread, and also the daily 100 ensemble analysis at the sea surface. The domain covers the domain is to the western North Pacific regions indicated by the red color, and the maritime continental region indicated by the blue color. And both domain systems have high resolutions of the 0.1 degree. So this is the summary, brief summary of the LORA and Jacob-2M and Abysso. The LORA is created by the regional ocean data assimilation system consisting of the SB-POM and LETKF. So here the data assimilation interval is so frequent of the 1 day, and the ensemble size is 100. And we assimilate a typical satellite and in-situ observations. And I also use the Jacob-2M ocean analysis dataset. And this Jacob-2M has a similar setting with the LORA, but a different data assimilation method with of the 3D bar. And I also use the Abysso dataset. This is a sea surface height dataset. And this is recognized as the best accuracy of the sea surface height dataset still now. So we move on to the result. This figure, I calculated the RMSDs of the zonal velocities relative to the independent drifter waves. The left panel shows the RMSDs, and the right panel shows the RMSD differences. The top is the LORA, and the middle is the Jacob-2M, and the bottom is the Abysso. So as you can see in the left panel, the larger RMSD is distributed around the cross-shear and cross-shear extension regions among the all of the three datasets. The RMSD differences shows that the LORA has a better accuracy in the mid-latitude region, especially around the cross-shear extension regions. However, the Jacob-2M is more accurate in the subtropical regions. And as I expected, the Abysso has the best accuracy among these three datasets. I also calculated the temperature, salinity, zonal, and meridional velocity RMSDs using the QOV located at the south of the cross-shear extension regions. The black line indicates the LORA, and the red line indicates the Jacob-2M. As you can see, the temperature RMSD, as you can see, the temperature is more accurate in the LORA than the Jacob-2M from the surface to the 300-meter depth. The deeper than the 300-meter depth, the LORA is less accurate than the Jacob-2M, but the differences is not significant. I think that this the limitation of the better accuracy in the LORA results from the prescribed vertical localization scale of the 100-meter depth. That is the cutoff scale of the about 400 meter. the salinity RMSD indicated that the Jacob2M is more accurate than the LORA, but the differences is not significant. And zonal and meridianal velocity shows that the LORA has a better accuracy than the Jacob2M, and this is consistent with the result in showing the previous slide. I also calculated the RMSDs relative to the Himari 8 SSTs. LORA and Jacob2M, both datasets uses this Himari 8 SSTs for the simulations. And LORA, Jacob2M, both datasets show the larger RMSDs in the higher latitude regions. This is probably because of the lower accuracy of the Himari 8 satellite in the higher latitude regions because of the larger satellite zenith angle. The RMSD differences shows that the LORA has a better accuracy, especially in the broad areas, especially in the mid-latitude regions. However, the Jacob2M has a better accuracy in Eastern Japan Sea and East China Sea.
1 minute, please.
Okay, thank you. So, so finally, I also calculated the RMSDs using the independent in-situ coastal SSTs. So you can see that the high RMSDs, the LORA has a high RMSDs over the 1.5 degrees Celsius. The differences of the this RMSDs shows that the Jacob2M has a better accuracies over the most of the stations. I checked the SSD time series at the location of the worst with the worst RMSDs. So we can see the higher SSD biases LORA has in boreal winter. So I'm now improving this high SSD biases, investigating the sensitivity of the atmospheric forcing with the high horizontal resolutions. So let me summarize the results. So we have constructed a LORA, the LETKF-based ocean research analysis in 2 domains, the Western North Pacific regions and maritime continent regions. In this talk, I only show the result of the Western North Pacific regions, but we have compared the, demonstrated that the LORA has a sufficient accuracy for the geoscience researches. This dataset, we are now planning to release this dataset in this year or the next year through the JAXA website. Thank you for your attention.
All right, thanks so much. It's really interesting, and I look forward to seeing it available. You mentioned in the beginning a little bit about the frequent DA and causing model shocks and imbalances and everything. And I was wondering if you could talk a little bit more about that. I see that you used IAU. Was it 3D IAU, 4D IAU? Yeah.
So I'm now using the 3D IAU. This is because easy to implementations. But yeah, the 4D IAU, if we implement the 4D IAU, the accuracy might be more higher compared with the current
Sorry.
current systems. Yeah, please.
I was just wondering if so the other, I don't remember the name, the Jacob2M. So they used a slightly longer data assimilation window than you're using, but did they see imbalances, do you know? Or is that because they're using a longer interval, it wasn't as much of an issue?
So you asked about the Jacob2M?
Yeah, I'm wondering if you know, or if you have seen any imbalances in that data set.
Yeah, so so first I would like to talk about the Jacob2M. The Jacob2M now using the 3D bar with the dynamical constraint of the geostrophic balance. But I checked the in the LORA, I check the dynamical imbalance. So I found that the combination of this RTPP and IAU is provide a significant improvement of the dynamical balance. So I adapted these combinations of the to improve the dynamical balance.
Cool, thanks. We have a couple questions coming in. I think we have a little bit of time. I'll go ahead and read. Lars Nerger asks, did you also check the transports in the reanalysis, like in the Kuroshio? This could give a more complete picture on the subsurface.
Sorry, I have not yet checked the transport of the volume transport of the Kuroshio and Kuroshio extension regions. Yeah, but this is the future work, I think.
Sounds good. Let's see. So there will be one more question in the Yopad. So if you wouldn't mind going there and taking a look at that. But I think in the interest of time, let's move on to the next talk. But thank you very much.
Yeah, thank you.